Science time. That sounded too sad. Let's try it. Everyone say it at once.
Science time.
Good. We're talking about two things today. We're talking about fluid dynamics and kinetic molecular theory. Which will be a nice change of pace because what we've been talking about until now is how bad I am at remembering to use the microphone correctly. So, great. Also, I have a sore throat, so don't sit too close to me and don't be mean about my voice. Let's talk about kinetic molecular theory first. One thing we like to do when we have a new phrase like this is break it down. You guys know about breaking it down. What's kinetic molecular theory probably mean? First, let's start from the back. What's a theory?
It's something that is believed in, but it's not proven.
Payton had said that, but I don't think that's the best way to describe it. Let's have another definition. Let's remember back at the beginning of the year, because there's a difference in the way that we use theory as human beings that is the definition Payton said. Like for instance, you might say, I have a theory that the grocery store closed at 4:30 yesterday. That's the kind of, what do you mean when you say theory in that case? It's not the scientific
something.
Yeah, you believe that. It's basically though a what?
Hypothesis.
It's basically a hypothesis. When we say theory in science, we mean I won't say the exact opposite, but it's much, much stronger. The scientific definition of theory. What is it? Do you remember from the beginning of the year?
Yes, I do. It's an explanation.
You studied it.
Yes.
An explanation
Yes.
of things or events based on
An explanation, and we're going to use this word, an explanation corroborated, we're going to have to break this down too, by a preponderance. Let me spell that better for you. I mean, it's spelled right, but let me write it in better handwriting. Of evidence. Okay, hold up. Now let's break this down. Explanation. What do we mean by explanation? What's it doing?
Explain.
It's explaining. As opposed to what? Remember, a scientific law, only what other verb? It doesn't explain. It doesn't explain why something is. It just describes the way it is. So like the law of gravity describes what gravity do. The theory of evolution explains how evolution occurs. Okay? So it's an explanation, first of all. Corroborated, what's that mean? You should know that, where we talk about that sometimes. What's corroborate? If I ask you to corroborate a math problem, what does that mean?
solve it.
Yeah, it means agree with. Like I'm asking you to do the math problem to see if mine is right. So that it's corroborated. All of the evidence, the preponderance of evidence, which means a big body of evidence, a big old fat sweaty body of evidence, all of the evidence that we have corroborates, agrees with this explanation. Okay, so that's what a theory is. It's not the opposite of how we use it in our daily lives, but it's much, much, much stronger in science. This has to be based on all of the evidence that we have. It has to line up with all of the evidence. If there's even one piece of evidence that doesn't support this theory, the theory has to be changed or even rejected. So a theory is an explanation that is corroborated, agreed upon, by almost all of the evidence. All of the evidence. Yes, Peyton.
Is the kinetic theory like the kinetic molecular theory?
Yeah, the kinetic molecular theory is going to be an explanation of what's molecular? What's that going to mean?
Molecules.
Yeah, referring to molecules.
So it's the kinetic theory is how particles in matter behave. Is this how
And kinetic is meaning what? Kinetic here meaning referring to kinetic energy, which is energy of movement. So this is going to be an explanation
of the molecular
of how
structure.
molecules, of how small particles move, basically. That's what we've got out of this, okay? So we're going to be looking for an explanation, which is explaining why molecules move, or how, it's more than just particles we're really talking about, it's more than just molecules, we're really talking about particles. We'll talk about it in the next chapter.
What's the difference between molecules?
That's exactly what I was going to say. We're going to talk about in the next chapter how come this is really about particles and not just molecules. But hold on to that thought for now, because we will come back to it. If you're dying to know, you could look it up on the Google, or you could watch, I have YouTube videos about it, but there are also good YouTube videos about it. So this is talking about how particles move. And not just that, but the explanation for why particles move the way they do. There are 4 suppositions of the. What does supposition mean? What's the root word of supposition?
Down. They go under.
That would be subposition, but this is supposition. What is the root word of this? Do you suppose?
Position.
No.
Sub.
Do you suppose?
So.
It's suppose. It's suppose. It's the four things we suppose about the kinetic molecular theory. Here are the things we suppose. 1. All matter is made of small particles. Does the evidence support this? Does the evidence corroborate this idea?
Yes.
Yeah, it does. All the evidence we have supports that all matter is composed of small particles.
What else would it be?
Yeah, right. Yeah, that's
Well,
exactly.
At one point in time, they all believed it was.
We don't. Right, and that's exactly the opinion. Is that at one point in time, no one knew this was true,
No one cared to know.
and no one cared because they had, they were getting trampled, or starving to death, or their children were starving to death, or they had diseases, but whatever. But now we understand that this is true because the evidence supports that. And then these particles, the particles are in constant. What's that word mean?
Not
Never stopping. Random. What's that word mean?
crazy.
Yeah, no set direction. Motion. They're in constant random motion. The particles collide with each other, which would make sense if the particles are in constant random motion. Of course, they're going to collide. And then 4, your book doesn't mention this one, but 4, the energy is transferred in the collisions. And we call this elastic collisions.
Wow.
Thanks, Justice. It is wow. All matter is made of small particles. I'm going to draw a little picture for that. I try to draw particles. The particles are in constant random motion.
You said it was elastic what?
Collisions. Elastic collisions. The particles collide with each other. And when they collide, the collisions are perfectly elastic, which means the energy is straight up transferred. There's none lost.
Energy can't be created nor destroyed, so
Energy can't be created or destroyed.
say some energy could be lost potentially if they weren't hit straight on, where would that energy go? Would it be collected by another one?
Where does the energy go? If this is actually, they're not perfectly elastic. It is mostly elastic. The energy is transferred. 99.99991, whatever. I don't know the actual amount, but almost all the energy is completely translated. Where does the rest go?
Just
To what? What do we know? It's the same way on the macro scale. Friction. Friction, yeah.
Oh, yeah.
So how does this differ for different matter? Is this true for all matter?
No.
Well, we've said that it is. We've said it's true for all matter, but it is slightly. None of these things is false for any kind of matter. None of these things is false for any matter, but the different kinds of matter have different behaviors within this. What are the? We had talked in the last chapter about the broad categories of matter. We had substances and mixtures, and then within mixtures there were homogeneous and heterogeneous, and those were broken down further. And then within substances there were elements and compounds, and those were broken down further. But what is another way we can classify all kinds of matter? All matter, you should know this from your chapter. Not this. You could say many different things, but specifically from this chapter, what are the other ways we can classify matter?
Like
The different whats of matter. These were vocab words.
Oh.
So we can break matter down into what it's made of, which is what we did in the last chapter, or the yes.
Plasma?
Okay, that's one of the whats.
Plasma, thermal expansion.
No, you guys know it. What are the different? Maybe my question is too big. I'm looking for the states of matter,
Oh.
or we sometimes call them the phases
So
of
like
matter.
chemical.
No, like solid,
Oh, that's what I meant.
liquid,
Solid, liquid, gas.
gas. There are more. What's the other one that we are forgetting? This
A
Gas.
solid liquid.
solid liquid. No? Another one. Your book even talked about it. I'm surprised you don't have this already in your... You should have this in your book. I know you do. Someone's already said plasma. Yep. And there are others too. There are other states of matter. There's something called Bose-Einstein condensate. There's something called superfluid. But these are the main ones that we talk about most of the time. In the universe, which of these is the most common? Be careful. In the universe.
Liquid. It's liquid.
Nope. In the universe.
Gas.
Nope.
What?
It's meant to be plasma. Why is it plasma? You know, you were just guessing the one that was left.
Just guessing the one.
Why? What's made of plasma?
Everything.
Not much. Not much here. There's no. These are LED lights, so there's not. There's plasma inside of fluorescent lights. There's plasma inside my plasma ball when it's on. Heat is not a substance, but plasma. It has to have a lot of energy. They have to be hot for it to be plasma.
The whole universe
Like
outside of the
light.
Earth. It's
Now, light is energy too, but what is
space?
fluorescent lights are
Stars?
plasma? Stars. That's exactly it. Stars are made of plasma, so most of the matter in the universe is plasma because stars are in the state of matter plasma. The reason I bring that up is because it's going to be a question on your test. It's going to say, which is the most abundant state of matter in the universe? And you're going to say plasma because of stars. Because you know that the sun is...
A huge star.
You know, like if the Earth were the size of my cup of coffee, the sun would be bigger than this room. You know, it's a huge thing. That's just in the solar
And
system.
it's not even the biggest star out there.
No, it's not even anywhere
There's,
near the biggest star out there.
It's called like the big...
No one knows what the actual
blue
biggest star-
one.
The biggest one we can see. There, you can look this up on YouTube. But I can forget the name. But anyway, you can look it up on anything you want. It doesn't have to be YouTube. Non-sponsor. The stars are made of plasma. But what's probably the most common state of matter on Earth?
Gas.
Liquid. It's got to be liquid because there's
It isn't
water.
either of
Like
those.
89%
What's
water.
the Earth itself usually? Most of it is solid. I mean, the asthenosphere is kind of a solid liquid, and then the inner core is solid, but then the outer core is a liquid. So it's mostly solid. It doesn't really matter. That's not on the test, and it isn't necessarily true. Let's talk about these things and how they relate to this. That was the original statement. So how do these phases of matter, how do these four suppositions of kinetic molecular theory change with the four states of matter? Well, are they all in constant random motion? Well, they must be, because that was one of our suppositions. All matter is in constant random motion. Is it all made of particles? Yeah. What could be different, though? You should remember this from your book. Yeah, not just how fast, but the kind of motion. So let's put, in this little column next to it, let's put the kind of motion. How do you think the motion is in a solid? What are the particles doing in a solid, if you had to guess, which I'm making you? They're not staying still, because they have to be in constant random motion. But they aren't moving from place to place, if that's what you mean. They're still moving.
The buzz.
Yeah, they're buzzing. What's another word we can use? Vibrating. I'm going to say vibrating. They're vibrating. They're moving, but they're moving in place. Wiggling back and forth in random directions, but in place. Like you jog in place. I'm not going to do that because I want to make a fool of myself in front of the video, but there can be motion of a particle without it actually going from place to place. You see what I mean?
Yep.
Vibration. Oscillation, we could call it.
How can water not be considered the most common on Earth if it's like the Earth is made of 89%
Yeah,
water?
The surface of the Earth is
Surface
covered
is
in
89%
three-quarters water.
Remember
But the Earth itself is made of, there's a lot of Earth besides just the surface. Okay, speaking of water, which is usually a liquid or a liquid on Earth's surface, how would you say the particles are moving in a liquid?
They move kind of loosely.
Yeah, they move loosely. They can be a wave. I'm going to put flowing.
Yeah, I said.
You can use whatever verb you want, as long as you understand that they can slide past each other, really.
Yeah.
In a gas, what verb could we use for that?
Really fast. Like
They would be moving
bump
quickly,
into
more
each other
quickly.
and everything.
Yep, bump into each other. I'm going to put bouncing. They do bump into each other and bounce off. And then, in this one, I don't have enough room to write this, but I'm going to put here I'm going to put ionized. Sorry, not deionized. Ionized, which is just that ionized. What's happening to the energy? If I have one kind of matter, does it have more energy as a solid or a plasma? Plasma. So this we could say, if I drew this arrow here, this is increasing in energy, right? This arrow is increasing energy. What do we have to do if I want to make this coffee, which is a liquid, mostly water? If I'm going to make this coffee, which is a liquid, into a gas, what do I have to add to it? Do I have to add energy or do I have to remove energy? Add energy. And how do I do that? Usually through heat. I would probably boil this if I wanted to make it into a gas. What would I have to do to make it into a solid?
Freeze it?
Yeah, freeze it, which am I adding or removing energy?
Removing.
Removing heat energy. All right. So these have an increasing energy. If I had a gas, if I made my water vapor out of this coffee into a gas, and I kept heating it up, instead of being 100 degrees Celsius, now it's 50,000 degrees Celsius. Eventually it would have so much energy that the electrons, remember the parts of the atom? The electrons would separate from the nuclei, and that's what a plasma is. So in that little plasma ball, that's exactly what it does. There's electrical current that provides enough energy to the gas in that plasma ball that the electrons are separated, and then that causes it to glow.
Can you get sick from too much plasma in the area around you?
There is not plasma in the area around you. If
consider
for instance, if there was somehow, like if there was a piece of plasma teleported into this room, it would be so hot that first of all, it would instantly cool down to be a gas. And depending on the amount, it might vaporize everything in here because it just has to have that much energy. And then in this column, I'm just going to put, so we have, this is how their movement is, and this I'm going to put the strength of their bonds. And this is just going to be the strongest bonds. This is going to be the weakest. And this, there's so much energy. Put bond strength here. Sorry, this is not very neat. Strongest to the weakest, and then this one has no bonds. In fact, not even the intermolecular bonds. The electrons themselves aren't bonded to the nuclei.
You said the solid and liquid is strongest?
Solid is strongest, and then it goes to gas, which is the weakest, and there are no bonds at all in plasma. And the last thing we're going to talk about today, we didn't get even as far as I wanted to, but the last thing I want to talk about today is the names we have for each of these. When a solid becomes a liquid, what do we call that? You remember? You know?
Water cycle.
Yeah. What is it called though? If I had a solid.
Melting?
Yeah, melting.
Melting point.
Melting. Not melting point, just melting. When a solid becomes a liquid, it's called melting. What about when a liquid becomes a gas?
Vaporize.
I'm going to call it vaporization because vaporization would also, in my mind, include boiling. And then a gas to plasma, you don't know this one, but a gas to a plasma is called ionization. I mean, we did use that word a second ago. Ionization. And there's also one for solid to gas. And that one, you should know this because it's a vocab word, but that one is called sublimation. Is this easy enough for you to see? You can't see it at all. I'm looking at the video right now. You can't see it at all in the video, so hopefully you're listening.
Solid to gas is what?
Solid to gas is sublimation. That one's cool because you don't think about it happening very often. But for instance, like we have an ice maker in our fridge, and I can tell which ice cubes are the oldest because even though the fridge is below freezing all the time, none of them can melt. But they get smaller and smaller and smaller as they get older because they sublimate. They just turn into water vapor on their own. If it's freezing cold like it is outside, and you put some wet clothes out on the line to dry, they'll still dry because of sublimation.
Isn't that what dry ice does?
Yeah, dry ice sublimates. Dry ice is CO2, which is not H2O.
Yeah.
But it sublimates. And there's in the other direction, we're running out of time, so I'm just going to lose the same, and you can watch the video again. But from gas to solid is called deposition is what that's called. When it goes right from a gas to a solid, that's deposition. These are vocab words. From plasma to gas is called deionization. From gas to liquid is called what? You know? If there's a gas and it turns into a liquid, that's called condensation. And then liquid to solid is called, you know this one too, freezing. Do you have questions? We've run out of time, but do you have questions about any of this before you go? Okay, that was lesson 1.
What was gas to liquid? Gas to liquid?